Hi everyone, I'm Baptiste. I'm a French PhD student, and today I'm really glad to talk to you about implicit UVs, real-time semi-global parameterization of implicit surfaces. And this is a joint work with Pierre Gueth, Jérémy Levallois, and Wang. So, the core of this work is implicit surfaces. As you probably know, they are defined as the zeros of a scalar field. And the great thing about that is that if you change the values of the field, then the entire shape might change. And so this makes it very useful for geometric modeling, for example, because you can very easily combine multiple shapes together. And it's also very useful for shape optimization, because you can simply optimize for the field and see the result on your shape without caring about its topology, which is very useful. And so these advantages of being able to easily transform your shape is really what makes implicit surfaces great, and that's what we want to preserve at all cost. But so, if the shape is not presented explicitly in a computer, how can you even visualize it? Well, when your field is a distance field, there is an algorithm that is known as the sphere tracing algorithm that allows you to compute the intersection between the ray and your shape without any kind of viscotization. And so the great thing about that is that if you can implement it on the GPU, which means that each pixel will shoot a ray and then you can color your screen to visualize your shape. And since it's implemented on the GPU, if your field evolves, you can see your shape evolve in real time. And so this means that sphere tracing is a rendering mode that preserves the advantages of implicit surfaces, and so that's why we want to work within this framework. Okay. But so this imposes some strong constraints on our work. Everything that we are going to do will be implemented in a shader, so everything must be pointwise and evaluatable in parallel. It must be super lightweight, because it's on the GPU, and of course you never want to mesh the surface to remain implicit. Alright? And so here's the main problem. Implicit surfaces are great to represent the geometry of a shape, but when you visualize your shape, how can you color it? How can you control its appearance? And that's really what makes it super hard, and what we want to be able to do on implicit surfaces, because it's the main reason why implicit surfaces are not widely used by artists, is because it's really hard to control their appearance. And because the thing is, what we can usually do with meshes is simply unfold them onto the plane, to unwrap it onto the 2D plane, and then to compute at each vertex of the mesh a UV coordinate, and then during the rendering we can fetch the coordinates at any point of our shape to control its appearance. And that's the thing that was really hard to do with implicit surfaces, and that's exactly what we want to do here. Alright? And because with meshes, a 3D mesh is a three-dimensional object that tells you that intrinsically it is a 2D object by nature that simply lives in 3D space, but it's a 2D object intrinsically. Okay, and so this 2D nature is described by its connectivity and the connectivity between the faces, etc., etc. And because, on the other end, implicit surfaces, even though theoretically they may represent surfaces, in practice you can only access to them through a volumetric query, which makes this problem it's like the main contradiction of the problem, which makes it really hard. But so from this observation, we need to first build a tool to be able to explore the surfacic nature of our shape, and that's exactly what we are going to build first, right? A way to move along the surfaces. So suppose that you're at a point P and you want to follow a tangential direction V. There is no closed form formula to do that for every implicit surfaces, of course. So what we are going to do first is work along local approximations of our shape. So a first approximation is the tangent plane, which is defined as the orthogonal of the normal vector. And you can simply walk along the tangent plane, right? But this will give you simply another one approximation, which means that we are going to leave the surface very quickly, right? As you see here. And so our first idea is to replace this simple approximation by using curvature information to build a local quadratic patch along which we can walk for much longer while remaining on the shape, right? Because this gives you another two approximation. And so if you want to walk for a long time, you can simply approximate your shape, walk, possibly reproject, approximate, walk, etc., etc. All right. But so if you think about this, from what we have built here, haven't we just solved the problem? Because we just found a way that I can associate with every tangential direction, which is like the set of the tangential directions at a point on a surface is a 2D space. It's a 2D plane. It's the tangent plane, and so we can associate with each tangential direction a point on the surface that you obtain by following this direction. And so this means that the fact of moving along the shape defines a mapping from the 2D plane to the surface, which is precisely the definition of a coordinate system. And so yes, we could compute UV coordinates this way. But the thing is, in practice, we need precisely the opposite of that. Because in practice, during the rendering with the surface tracing, there is going to be a ray that is going to hit the surface at a point X, and we would like to be able to compute, like, what's the UV of the point X in the referential of the point P. And once we have that 2D coordinates, we can now fetch some textures, okay? And so if the forward map, which is to follow a direction, is the exponential map in differential geometry, we want to compute the inverse of this map, which is the log map, all right? But the thing is, the exponential map, it's super easy to compute. You simply start from a direction, you simply start from a point, and you follow a tangential direction, which is very easy to do, as we saw. But the opposite map is much harder, because it actually amounts to finding a shortest path between our 2 points on the shape, which is much harder. And even more so, since we don't build a mesh, we don't have a shortest path algorithm, right? And so, since we are running with very limited resources, we don't have a global view of the shape, we cannot do global algorithms, so we are going to have to use an approximation and a heuristic to guide our path. And so the idea is very, very simple. Suppose that you are at a point X and you want to reach the point Y, at which you want to compute what's the coordinate of X in the referential of Y. Okay. A first idea, ideally, you would like to follow the vector Y minus X. But if you do so, you're going to leave the surface immediately. And so first we project this vector onto the tangent plane. Then we follow our second order approximation. And this gives us a first iterate. And we can repeat this process many times until we reach our point Y. So this may be seen as very simple, but in practice there are some technicalities that are quite hard to grasp. I invite you to check the paper, but an example is that when you do that, you want to be able to, like on the GPU, you cannot use a while loop to do that, because you cannot have while loops on the GPU. And so you want to do a for loop with a given number of steps. And importantly, all the points all the points X needs to take the same number of steps to reach the point Y, because if you have a different number of steps for different points, you're going to have discontinuities in the UV, which is a bad thing. But anyway, this gives us a process to compute a curve gamma between our 2 point X and Y, and we are going to see how we can compute coordinates from those. So first, the length of the curve gives us an approximation of the geodesic distance between our 2 points. Then, if you fix a reference frame to the point Y, you can compute the angle between the curve and the frame. And then, since we have a length and an angle, we can draw inspirations from polar coordinates to convert this angle and this length onto the UV coordinates, right? And if you think about it, this gives us, we never discretize the shape, and we can evaluate it point-wise in our setting, so it works. And as a point of vocabulary, we are going to call the triplet Y, E1, E2 a seed of the UV field. But first, the fact that we have an entire curve between our 2 points gives us much more information about the shape that simply coordinates. For example, there is something that is known as parallel transport, and that tells you how a tangent vector that lives at X will transform when you move it along the curve gamma. And so we can discretize it by simply accumulating a rotation matrix that aligns each normal vector of one iteration to the normal vector of the next iteration. And at the end, what you get is a rotation matrix that maps the tangent plane of X to the tangent plane of Y. And as we are going to see, we are going to use this tool later. And another thing that is very important is that you might have noticed that the way we walk along the shape assumes that the shape is smooth, or that f is differentiable to build our local approximation. But of course, it's not always the case, right? So our method cannot cross in a way that is robust sharp features. But what we can do is we provide a very simple trick to detect discontinuities, to detect sharp features, and to stop the computation. And so we simply say, if I detect that an angle between one normal vector of one iteration and the normal vector of the next iteration is higher than a given threshold, then I can simply say that there is a sharp feature and stop the computation. Okay. And so this means that the surface is implicitly segmented into smooth regions of your shape. This may be seen that our method will work on an implicitly segmented version of the shape by sharp feature. And so this may be seen as a limitation, but actually we found that in practice, since sharp features very often delimit different semantic regions of the shape on your object, it's often very useful in practice during the UV editing process. Alright? But so, everything that you need to remember from here is that we have a way to compute a local parameterization at any point of our shape without discretization, and that can be implemented in a shader. And so this means that you have an amazing level of control and interactivity, because everything is recomputed at each frame for each pixel, and so it means that you can change any parameter of anything. If you want to still edit a bit your shape, or if you have to change any parameter of a method, like a position of the seed, or even if your shape has to evolve, you can do that. You can do that without problem. All right, and so that's great, but as you see, one seed is not enough, right? Because it is known that the log maps accumulate distortion with curvature, and of course, when the geometry gets complicated, our heuristic will have some limits, as you can see here, for example. Here are some points that were not able to reach the seed Y. And so a first solution is very simple. You can simply say, well, I'm simply going to place multiple seeds on my shape. And when there are multiple seeds, I will keep the UV of the seed that is the closest to the query point X, but with respect to the geodesic distance, right? And so because we have an access to an approximation of the geodesic distance. And this makes a huge difference, because compared to previous methods that were completely the implicit decals method by De Groot et al., that were only using the ambient space, they did not take into account the geometry of the shape. And so as you can see here, when you do that, you don't have you don't keep any information about the geometry and the topology of the shape, and so you get some very incoherent UVs, some UVs on the shape. And here, since we have an estimation of the geodesic distance, and on top of our segmentation by sharp feature, as you see, we get something that is very coherent. All right, but so that's nice, but it's already it's enough to paint on the surface. But the thing is, it's not practical to apply structured textures, because as we can clearly see here, there are a lot of discontinuities. And so for very structured textures that are not like noise, like this one, it's those discontinuity are very visible, and that's a problem. But one thing that would be very, very nice is well, what if we could remove the discontinuities? What if I could select multiple seeds together and merge them to remove the discontinuities between them? And so that's exactly what we are going to build, and it's our main contribution, right? So we are going to merge multiple UV fields together in a way that remains pointwise. And we are going to do that by taking weighted averages of coordinates. But first, very simply in terms of workflow, so you can interactively place your seeds on your shape, edit a merging graph to tell which seed do you want to blend together, and this involves some very small computation on the CPU. And once they are done, at each iteration, the graph is sent on the GPU in the shader, so that the algorithm can know with which seed he needs to blend. Okay, so very simple workflow, very simple to control. But so how can we do that? Well, first, there is a problem, because we said that we are going to do that by weighted averages, but we cannot take weighted averages of log maps, because log maps, as we saw, are relative coordinates. Each point Y tells you what is its view of the point X in its own referential. And so each one, each log map lives in its own referential. And so what we need to do first is to be able to express every log map in a common coordinate system, in a common UV space, right? So this means that we need to place the root, the seed, each seed at a spot in the common UV coordinate system. And once everyone is in the same referential, now we can take some weighted averages to remove the discontinuities between them. But so now we need to figure out what kind of weights do I give to what seed, and how do I compute those UV offsets to bring everyone in the same referential. And so first, when I say we are blending coordinates, I'm not talking about stuff like triplanar mapping when you blend the colors of the textures, right? I'm really talking about blending the UVs together to remove the discontinuities and to extend the range of validity and quality of our fields. Okay, but so first, how do I compute those weights? So I don't have the time to go into the details. You can check everything in the paper, but we are going to use compact support interpolation, which means that we only blend at the interfaces between multiple seeds. Like if you're close enough to one seed, you only keep its UV, and only when you get close enough to the frontier between multiple seeds, then we start to blend. Okay, and so the way we do that only depends on the geodetic distances between the points, and very importantly, we have a very simple test to avoid, like we have a simple test to check if another seed has any chance to have an influence on the result, and if it's not the case, then we can simply avoid to compute the geodesic to that seed to save a lot of time. All right. And so that's for the weights. And now how do I compute those UV offsets that we use to bring each seed in the common referential? Well, since every log map is computed from a reference frame, we need first to compute a reference frame for each point that is as compatible as possible with its neighbors. And so what we do first is computing the smoothest vector field onto our merging graph, which we can do by minimizing a very simple quadratic energy that simply will penalize the difference between each like the vector of each node compared to the vector of its neighbor, right? So we penalize this difference. And once we have computed the smoothest vector field, we can simply complete it into a frame field on our graph by a 90-degree rotation. Okay? And so that's it from the frames. Now we can compute the log map of each seed, and we are going to compute the UV coordinates very simply as like the UV offsets are absolute coordinates. And so what we want to do is to compute them, it's to fix their values such that the difference between those two absolute coordinates are as close as possible to the relative point of view that each seed has to its neighbor. Okay. So once again, more details in the paper, but what is important here is that those are two very simple quadratic energies. And minimizing a quadratic energy, which means that you can simply solve a very simple linear system that is sparse and symmetric positive definite. So we have very efficient solvers, but on top of that, you might say, well, if you have to solve linear systems, that you cannot be real time anymore. But the thing is, we have to compute one frame per seed and one UV offset per seed. Okay, and so the size of the linear system is the size, like it's the number of seeds that you want to merge together. And in practice, as you see here, we really don't need a lot of seeds together, and so in practice it's like really more than 10. And so you just have to solve 10 by 10 linear systems, which we can do absolutely instantaneously on the CPU. So everything remains real time, and we have a full control over the global UV field on the shape. All right, and so this is recomputed at each, like only when the graph changes, and so yeah, real-time editing. Okay, but so this is great. This allows us to compute like a global coverage of high-quality UVs on our implicit surfaces, and now we can dive into the applications. So a first application is, of course, rendering. It's very simple to apply textures, like to load some colors, to use some specular maps, etc. And we can also use normal maps by using parallel transport. Okay, and so it really gives you a lot of control over the appearance of your shape. And so that's nice, but we can even do more by using displacement map. Like a displacement map is a deformation of a shape in the normal direction. Okay, but the thing is, this means that we need to be able to transmit the information of the displacement from the shape to the entire field. All right, and it's a problem, because if we don't transmit the information in the entire field, then the sphere tracing will not be able to see the displacement, and so we will get some really weird artifacts. So what we're going to do is that each iteration of the sphere tracing, we first project the point onto the shape, then we compute its UV, and then we can modify its distance as the original distance minus the height of the displacement. And so this effectively transmits the information of the displacement in the entire field. And so, of course, when you can bound the height of the displacement, you can simply perform the computation on a shell around the surface. But so yeah, this means that you still have to compute UVs at many iterations of the sphere tracing algorithm, and so this means that it can be quite expensive. Like when you want to add some details on an already complicated shape, you might not be able to render it at a very high frame rate, right? So this can be expensive. But another application that we find super promising is to do the opposite. Instead of adding details on a complicated shape, you can encode a complicated shape as a deformation of a simple one. Okay, like here we encode a head as a deformation of a sphere, and so we can bake the textures and the height and the displacement map to do this morphing, and it's super fast because it's only you just have to compute the intersection between rays starting from the sphere to the head, for example, and we get that. And since here we only evaluate the SDF of the sphere, this runs super fast at 60 FPS. So really, that's really promising. But like those two shapes, like they look nice, but what you need to remember most importantly, or like the main contribution, is that we never built a mesh. So everything that you see here in our results remain implicit. And so this means that you can still do all the stuff that we love with implicit surfaces. You can still combine them, you can still use some warping, you can plug in our parameterization system in a CSG pipeline, etc., etc. and in real time, so that's really nice, and that's really what you cannot do with meshes. Like you could not compute topological intersections in real time with meshes, right? And so that's really great, and that's our main contribution. And you can do much more than that. You can do implicit shell maps to extend our 2D coordinates from 2D coordinates, to a 3D shell around the shape, which is really great for geometric modeling. And another application that you can see in the paper, for example, is some vector field interpolation, which is quite nice for texture generation, for example. All right. And so to conclude, we introduced the first method to compute UV coordinates on implicit surfaces without any kind of discretization, and that runs in real time in a sphere tracing pipeline. Then we show that it allows you to combine the advantages of implicit surfaces, like implicit representations, and get the explicit control that you can get over your shape with textures, which is really the most promising thing about that. And of course, the limitation is that when you have a very complex geometry, you have to place a lot of seeds, and so you can see a decrease in performances. But kind of a counter-argument to that is that you can replace your complicated shape with a simpler one with a normal map, as we do with meshes, for example. And there are, of course, a lot of room for performance improvement, most importantly because when we walk along the shape, we just need to evaluate the local characteristics of our shape. And so we don't need the entire SDF, and so if you have some kind of system to only evaluate the SDF of the neighborhood of a point, then you can get some amazing speed up for this technique. And so a future work, of course, is the automatic placement of seeds on the shape and the automatic generation of the merging graph, right? And so that's it. Thank you very much for your attention, and I will conclude this talk by this example of a very simple texturing of a shape. And so as you can see, it's very simple, very intuitive, and very simple to build a global coverage of some shapes, right? And I was asked that at the conference, but here what you can see is simply a difference in the fact that those cells are much bigger than those ones. It's not a distortion. It's simply that it's the pattern of the texture, right? It's a crocodile skin, if I'm not mistaken. And so that's it. Thank you very much for your attention. And if you have any question, please reach us. Thank you.